A really satisfying holiday needs a vision, a destination, and a cutting-edge, ultra-comfortable plane such as the Airbus A380, whose high-tech landing gear will reliably withstand extreme shocks as 560 tons slam onto the runway at the speed of a Formula One racing car. Home sweet home. Bright light shines at the flick of a switch, and an energy-efficient heat pump provides cozy warmth because, behind the wall socket, high-end technology in power plants and wind energy generators ensures a reliable supply of electricity, day in, day out. The cars of the future will increasingly feature electric drives. Especially hybrid cars have already become a common sight on our streets. Sophisticated electronic controls switch between purely electric cruising or dual power supply. The centerpiece synchronizing the combustion engine, generator, and powertrain is a highly efficient automatic gearbox. These everyday examples highlight the key role of forged components in the landing gear of the airplane, the forged shaft of the power generator, the ring-rolled toothed rims in the wind energy generator, and the forged toothed wheels, synchronizing rings, and shifter forks in the car gearbox. Forged components can actually be found in most high-end mechanical products, especially in applications requiring ruggedness, precision, and reliability. In the powertrain of passenger cars, in engines and axles of trucks, in engines and shafts of ship machines, in traversing gears of railroads, for abrasion-resistant parts of mining equipment, in propulsion units of machines and cranes, in jet engines, but also in joint prostheses and surgical instruments for medical applications. What exactly makes forging so special? Forging exploits a unique feature of our industrial metals, their plasticity. For more than 2 million years, mankind had to rely on stones, a subset of minerals in general, as its main tool material. Stones cannot be deformed, they break and splinter. In stark contrast to this, industrial metals can sustain substantial deformations without breaking. The earliest smiths used hammer and anvil. Initially, both were made of stone. As long as 10,000 years ago, mankind used such tools to hammer lumps of native copper into the desired shape. Over time, this craftsman's work evolved into numerous other processes, such as rolling, drop forging, flow forming, upsetting and extruding. Processing is applied to virtually all industrial metals such as steels, copper, brass, aluminum, as well as nickel and cobalt alloys. The common characteristic of all forging technologies comprises major cross-sectional changes, mostly reductions. This is a key distinction from other forming technologies such as sheet metal forming. The predominant forging process is drop forging. The die is generally a two-part female tool made of high-strength, heat-resistant steel, which is mounted on a strong machine. Subsequently, a red-hot rough forging is inserted. When the tool closes with enormous pressure, the hot metal will plasticize and flow into the cavity of the mold. Excess material from the rough forging flows into a residual slit between the die halves and forms a ridge, which will subsequently be removed. The reopening die releases a forging with the desired shape. The degree of deformation is limited by a number of factors. Forgings with complex or intricate shapes thus often require several forging steps using sequenced tool sets, each performing a limited portion of the total forming process. The final contour will only be achieved by the last process step. Open die forging resembles historic hammer forging, but nowadays the tools are much more powerful. Forging is performed by repeated press strokes with a tool fixed to the crosshead. Like the anvil, this tool will often be flat, but it can sometimes be semi-shaped to better accommodate the contour of the forging. Between the press strokes, the forging is constantly repositioned. This time-consuming procedure makes open die forging significantly more expensive than drop forging. For this reason, it is mainly applied if batch sizes are too small to justify the expenditure for the production of a die. Another important application field is for parts that are too big to be formed in a die, such as crankshafts for ship engines or shafts for power-generating turbines weighing more than 100 metric tons. The flow forming process is characterized by a tool exerting such a high pressure on the rough forging that the material plasticizes and flows like dough. There are several variants of the process. In the case of teeth for dredger shovels, the hot metal is pressed into a steel die forming its outer contour, while a protruding core will shape its cavity. In other cases, the material is forced through a tight opening, shaping its contour, as for fancy shortbread biscuits. Furthermore, there are a number of additional variants. Shaping is often performed in several steps and may even involve different process types. This results in the production of sometimes very advanced components, such as intricately shaped hollow shafts for gearboxes. Flow forming is often performed using complex, highly automated plants featuring outstanding productivity. Machine and plant builders need seamless rolled rings made of high-strength materials for a broad range of applications, such as circular tracks for cranes, bearings and gear wheels, through to railroad and wheel tires. They are produced on sophisticated ring-rolling plants. Rough forgings are made from forged and subsequently pierced discs. Ring rolling requires advanced plant control systems, since the thickness, width, and diameter are interdependent. Steels are by far the most prevalent material group in the forging sector. They are inexpensive, easy to process, and can be alloyed and heat-treated to achieve the highest strength in combination with superior toughness. Moreover, steel parts can easily be recycled at the end of their life cycle. The high strength of steels often makes it easier to attain optimized solutions with respect to vital aspects such as weight reduction and enhanced efficiency. The alloy range is very broad, stretching from low-cost carbon steels up to high-alloy stainless steels. Second in rank among the materials processed by forging is aluminum, which is of particular interest for the automotive sector. Here, aluminum is used in undercarriages as well as for safety applications such as crash boxes. Furthermore, numerous other industry metals are forged. For example, the highly temperature-resistant metals nickel and cobalt are used in airplane jet engines. Airplanes also feature forged structural components made of titanium. Forged brass is used for synchronizing rings in gearboxes or for fittings. The list of metals processed by forging also includes copper, magnesium, and lead. Modern forging is a complex high-end technology whose products meet the highest requirements with respect to strength, reliability, efficiency, and value for money. In order to achieve these aims, the forger has to excel in a broad range of disciplines, such as material sciences, design engineering, process technology, production planning, and engineering, machining, and quality assurance. To this effect, he uses cutting-edge computer-assisted software tools. Of course, a particular focus is placed on the computer-assisted modeling and simulation of all phases of the forging process, from the direct input of 3D CAD design data from the customer to the definition of the necessary forming steps through to the design of the required tools. This includes the definition of vital processing criteria such as stress levels of tools and working parameters of the plant. This strategy makes it possible to detect any weak points in advance and to correct them by means of design changes, if necessary. The related software tools have, in the meantime, reached such a degree of maturity that it is now possible to design the operations of single plants on screen and to subsequently group them to complete production lines. Advanced features even include operations such as downstream machining or checking the size and frequency of quality assurance measures. Furthermore, computers can even perform the modeling of assembly operations as well as the integration of modules to complete systems. Using such tools results in highly efficient, cost-saving, and securely manageable production processes, yielding sturdy, reliable, high-tech products at the highest quality level. As a result of this in-depth engineering competence, the modern forger acts as a fully valued partner of his customer for the development of new products. His knowledge about the viabilities and limits of his processes is a crucial asset during the design phase of new products. While the designer of the customer will initially define a basic geometry as well as the corresponding set of requirements, the forger will contribute his knowledge about alloys and processes in order to optimize material selection and the production process approach. This often requires a makeover of the original design. This is best done if the designer hands over just a coarse definition of the part shape, as well as package geometry boundaries, interfaces, and the required mechanical properties. The next steps are then a computer-assisted optimization of the geometry and a suitable redesign, which in turn becomes the basis for the aforementioned design steps, from a finite element analysis of stresses and strains, right through to the design of the required forging tools and the configuration of the process chain. Further important services rendered by the forger include additional downstream value-adding operations such as machining, assembly to element groups and modules, as well as additional services from painting and packaging down to the complete supply logistics. This is in line with the requirements of important customers who want to focus on their core competences and thus tend to source in less vital parts of the process chain from their suppliers. Such customers are not interested in bulk ware. They look for suppliers able to secure the just-in-time supply of quality-assured, function-ready components directly to their assembly lines. Starting with the automotive industry, this trend has meanwhile spread to many other customer sectors, such as machine builders and manufacturers of power-generating equipment. The German hot and cold forging sector is the technology leader worldwide. This makes it a red-hot job opportunity, especially for young people with a penchant for technology. And with a total workforce of some 30,000 employees, excellent opportunities abound, especially for people with a technical background. The sector is looking for apprentices, skilled workers, and foremen of all metalworking disciplines, from locksmith and welder through to toolmaker, materials tester, and metallographer. Short supply also prevails for skills in mechatronics, metal cutting technologies, and technical drawing. The sector is also looking for personnel with higher qualifications, such as technicians and engineers. Here, too, the bandwidth is very broad and includes disciplines such as forging, ferrous metallurgy, material sciences, machine building, automation technology, design engineering, and informatics. Furthermore, there are jobs for mercantile skills, office workers, cost calculators, procurement and logistics managers, as well as specialists in the field of marketing and sales. Forging is a technology with great prospects because regardless of what challenges the future holds for our society, their solution will always have to include forging technologies. They are a prerequisite for any high-technology civilization. Especially in times of shrinking resources and energy supplies, even more intelligence has to be invested to further maximize the sustainability and resource efficiency of all industrial processes. This is a great opportunity for young people to actively participate in the shaping of the future of our civilization.